hi guys. So welcome to one of the video on chapter 9, transfer of thermal energy. Like I always mention in class, in this chapter we're going to look at three things: conduction, convection, and radiation. Okay, and in this video we're going to look at these three methods of heat transfer in much detail.
Today I'm going to bake this chocolate cake. Now those of you who know me know that the only reason I would do this is to prove a point. Earlier I was asking people to compare the temperatures of these two objects: a science book written by Isaac Asimov and an old metal hard drive. Can you compare their temperatures?
I'd say this one would be
Yeah, that feels colder.
Cold and nice room temperature.
Can
You
tell
would
me?
say colder than that one.
Yeah. What makes something hotter or colder? What affects that?
The actual material. I mean, paper is warm and metal is cold.
Both of these objects have been sitting here on the ground for quite a while, so one might expect that they're at the same temperature.
No, because this is a metal and that's paper.
But what if I left that outside all day? Would it be 15 degrees?
No, because paper doesn't absorb cold.
Doesn't absorb cold?
No.
Well, I've left books out not all day, outdoors, and I can't say that I've noticed the book was cold when I've come to pick it up. Ever.
What if I told you that these two objects are actually the same temperature? What would you say?
Definitely not. If you take a temperature right now, this is colder.
So let's say you're taking a cake out of the oven.
Yeah.
Would you be worried about touching the cake?
Yes. Well, not the cake itself, but the actual tin around the cake, because it'll be hot.
Yeah, but how does the temperature of the tin compare to the temperature of the cake?
Well, the cake will be warm, like hot, but not as hot as a tin.
The tin's hotter because it's metal. Metal holds the heat longer and holds the cold longer.
Like if
You
you,
don't
touch
think the tin would be the same temperature as the cake?
well, you think if it's been like in 200 degrees Celsius oven, it'd probably be the same, but it just doesn't feel like it will burn with metal, whereas my fingers will burn. But I mean, not if I stick my finger in the cake, it wouldn't burn as much.
Alright, it's time to take the cake out and find out if it's the same temperature as the tin. I have a meat thermometer with which to measure the temperature of the cake. I'm not sure that's the most accurate way of doing it, but, well, it's the only thing I've got. So let's give it a shot. So I tried to measure the temperature of the cake using a meat thermometer, but unfortunately its temperature scale doesn't go high enough to allow me to accurately measure the temperature of the cake. You can actually hear the moment when I realized that my experiment wasn't going to work. Uh-oh. So now I'm back in Vancouver, and I thought I'd bring in the big guns to help me sort out this experiment. And by the big guns, I of course mean my mom.
So, Derek, I understand we're going to make this vanilla cake mix together and see what happens.
We've got a secret weapon, which is this infrared thermometer, which can measure temperatures up to 300 degrees Celsius, so we should have no problems with it. We just point it at a surface, and it gives us a readout of the temperature of that surface. So this should be perfect for measuring the temperature of the cake and the tin. Do you want to make a prediction about the relative temperatures of the cake and the tin when we bring it out of the oven?
Well, I really suspect that the tin's going to be a lot hotter than the cake. You can really not handle the tin at all. So I reckon that's what's going to happen.
Okay. Well, I think they're both going to be the same temperature, but I could be wrong. So we're going to have to do the experiment and find out.
All right, let's get mixing.
Okay, so it's been about a half an hour, and the cake is cooked. It's ready to come out.
Yeah, we're all ready to go.
That is your expert opinion as the master baker here?
Yes, I think so.
Okay, we're going to take the cake out of the oven, and we're going to check the temperature of the tin and the cake. Let's do it.
Okay.
Ooh, it looks like a good cake.
Yeah, not a bad one.
Okay, so let's measure the temperature of the cake. We have...
108.9.
And the temperature of the tin?
118.6, but dropping.
Over here?
108.1.
So we have, what would you say about the temperature of the cake and the tin?
Pretty close. Much closer than I expected.
They're quite similar. They're both around 110
Yes.
Celsius. That's my point, is that the tin and the cake are the same temperature. But the tin is going to conduct heat to your hand much faster than the cake. So the tin would burn you, but the cake would not. But they're the same temperature. What if I were to impress upon you that they are in fact the same temperature?
I'll take your word for it.
And that, in fact, that these two are the same temperature.
No, I don't agree with that.
You don't think those are the same temperature?
No.
Really? I just can't believe this book is 15 degrees. It just doesn't feel it. I just
doesn't-
can't believe it.
In truth, there's no difference in the temperature between these two objects. If they've been in the same surroundings for a long period of time, they come to thermal equilibrium with their surroundings, which means they're both at the same temperature. But the metal feels colder because it's able to conduct heat away from my hand faster than the book. So just because an object feels colder, that doesn't mean that it actually has a lower temperature. It may just mean that it's conducting heat away from your hand faster.
Why does heat transfer from hot to cold? Heat is a form of energy. When energy is added to atoms, they begin to move more rapidly. Think of it like kinetic energy. When you push a ball or add energy to it, it rolls. This means that the more motion atoms have, the hotter they feel to the touch. Back to the ball example. If you have a stationary ball and you impact it with another ball, the energy of the rolling ball is transferred into the stationary ball, causing it to move. You would say that the stationary ball absorbed the faster ball's energy. It wouldn't be right or sound right to say that the stationary ball transferred its stationary state to the rolling ball. The same is said about atoms transferring energy. The fast-moving atoms impact slow-moving atoms, transferring their kinetic energy. Therefore, to say heat transfers from hot to cold really means that energy is transferred from fast-moving atoms to slow-moving atoms. If you enjoyed this video, give it a like, be sure to subscribe, and check back next Wednesday for a new fact. Anyways.
Okay, so let's go. Alright, first thing over here, what is a conductor and what makes it good and bad? Okay, so I think I mentioned in class the difference between conductor and insulator, right? It's not about their temperature, but rather on the rate they transfer heat. Okay, so conductor is a material that transfers heat at a, for conductor it'll be fast rate. Okay, we're gonna use rate, fast rate, and for blue, right, it'll be slow rate. Okay, so two objects, right, maybe a conductor and insulator, both can be at like 25 degrees Celsius, both are at room temperature, but when you touch one and the other, you realize that one feels colder, right, than the other. Okay, although they are at the same temperature because they transfer heat at different rate. Okay, so what happens is maybe you are like at 35 degrees Celsius, right, and heat is going to transfer out from you, okay, because heat travels from a higher region here to a lower region. Okay, so either of these two. So what happens is that because you are touching a conductor, heat is going to flow out from you at a faster rate, and because when you touch an insulator, heat is going to flow out from you at a slower rate. This part here makes you feel colder, right? Okay, so for conductor, you are actually going to feel colder because heat is coming out from you at a faster rate, and for insulator, you are going to feel that it is slightly warmer. Okay, so in the experiment that I did with you all in the class, when I asked you to touch a piece of metal and I asked you all to touch a piece of paper, or rather to touch the book or something, all right, I think you all have all concluded that the only reason why the metal feels colder is because it transfers heat at a faster rate. Okay, so this is nothing new, but this is one of the most important concepts in heat transfer when we talk about conductor and insulator. Okay, I don't want anyone to consider that conductor is always at a lower temperature or at a higher temperature, okay, because that doesn't make sense. Okay, yeah, so over here explaining using heat, idea of heat transfer and rate of heat transfer, why people touching the metal felt a more cooling sensation compared to those who touch a wooden plate. Okay, so I think I explained this, so you can write this in your own words. Okay, but the main idea, right, is that conductor conducts, okay, maybe not conducts, allows a greater rate of heat transfer as compared to insulator. So with that, okay, you'll be able to realize, right, that you will get 1 point here. Now the other point that you will be getting is when you mention why you feel a cooling sensation. Okay, so like the cooling sensation comes when heat is transferred out from your body, right? So if heat is transferred at a faster rate or greater rate, you know, you're going to feel a greater cooling sensation. Yeah. Okay, and for quick check 1, if you need to pause the video, please pause. Okay, but anyway, the stone floor feels colder than the carpet. Okay, in other words, stone is a better conductor as compared to carpet. Alright, so if it feels colder, it means heat is flowing out from our body, right? So I don't think A and D are correct. Okay, so let's just look at B and C, right? More heat flows from the carpet to your foot, more heat flows from your foot to the stone floor. Okay, so flow from carpet to your foot, I think this is wrong as well, so the only answer is C. Okay, so first thing, heat flows from our foot to the stone floor, and more heat flows to the stone floor than to the carpet. Okay, so let's move on. Okay, I think this is similar to this question here. Okay, so I won't go through this question. Please try on your own. Okay, like craft your own answer, and if you want, you can check with me in class whether your answer is correct or not. Okay, I don't think you all will have major issue for this question here. Okay, so let's move on. Yeah, okay, so for this part, right, good conductor and poor conductor, I just want to bring your attention to a few materials. Okay, so copper is a good conductor. Okay, so remember copper and as well as aluminium, because these two metals are quite special. Later on in physics, maybe like Sec 4 or something, when we look at magnetism and electricity, we're going to look at these two metals again. Okay, and poor conductors are like your normal glass. Okay, there's like, I don't know why I wrote glass twice there, but okay, you don't really have to memorize this. Also, please remember that water is not a good conductor of heat. Yes. Okay. Wait. Yeah, water is not a good conductor of heat. Remember that the heat capacity of water is 4,200. Okay, so that's actually quite a lot. Okay, for the science physics students who do not know what heat capacity is, basically it requires like 4,200 joules of energy before you can gain 1 degree Celsius, and like that's actually a very slow rate of heat transfer. Okay, yeah. Okay, so quick check 2. Fiber is used for loft insulation as shown. Okay, how does fiber prevent heat from passing through the ceiling easily? Okay, so remember, maybe you want to add to one of the more famous one, materials containing trapped air. Air is a poor conductor, which is, in other words, right, air is an insulator of heat. Okay, so fiber is a material that traps air, and because of that, heat is going to transfer at a slow rate. Okay, and one of the reasons being air is a poor conductor of heat, and therefore if you trap air, the air is going to allow heat flow to be slower. Alright, so how does fiber prevent heat from passing through the ceiling easily? Okay, so fiber does not allow air to pass through easily. Fiber is not warm, fiber is not tightly packed. Okay, fiber traps air. Okay, if you do not know what fiber is, so okay, this is your fiber. Alright, your fiber mesh. Okay, and they trap air. Okay, I mean it's quite obvious how fiber is going to trap air. You see like the many vacant spots for air to be trapped over here. Okay, alright, so that's fiber. Okay, quick check 3. So in this case, right, if matter is a good conductor of heat, okay, when the hot air goes on to the metal door, right, okay, what happens is that the hot air will be easily absorbed by the metal. Okay, and in that case, right, the hot air will not be absorbed by the paint. So if it's not absorbed by the paint won't be able to be softened. Okay, but if this door is now made of wood, right? Okay, and then you have hot air going to it, because wood is a poor insulator. It's a good insulator of heat. All right. In other words, poor conductor of heat. What you get is that the hot air going towards the wooden door will not be absorbed by the door so readily. Okay, so maybe the heat will be dispersed to the paint, and this causes the paint to soften. Okay, and that's why the hot air blowers work better on wooden doors, and this is the reason why, because metal is a better conductor of heat. Okay, now please try these questions here. I will give you like the main concept here. You can please craft your answer on your own. Explain how the fur of a polar bear keep it warm. Okay, yeah, please pause if you need to. Okay, so explain how the fur of the polar bear keeps it warm. Okay, the fur keeps it warm because the fur traps air. And then you make, this is like the first point. And then when you talk about fur traps air, you talk about air being a poor conductor of heat. Okay, and then you talk like how is this going to affect heat transfer. Okay, now the floor part, we have done it several times already, so I'm not going to go through it. Okay, but still, explain why a marble floor feels colder compared to a wooden floor, even though they are at the same temperature. Okay, I think there's a typo here. Now the reason, okay, so I explained this a lot of time already. If you do not get it, please go back to your notes. This part, okay, the very first part, right? It's the same thing over here also, right? So please rewind if necessary. Okay, now explain which material is more suitable for a thermal flask, plastic or steel. Now when you make a thermal flask, right, what you want is that, be it cold or hot, you don't want the heat. Okay, let's say if it's cold, right? So blue signifies cold. Now if it's cold, I don't want heat to enter so readily to make my drink hot. Okay, now if it's hot, right, I don't want my heat to like exit so readily to make it cool, right? I don't want that. Okay, so what I want is also known as a slow rate of heat transfer. Now which of the material here gives me a slow rate of heat transfer, right? It has to be the insulator. Okay, so plastic is good, but most of the time you don't use plastic for thermal flask because it will keep hot drink, right? The plastic will actually start to melt, and this is harmful for consumption. All right, later on we'll talk about the thermal flask towards the end of the chapter. Okay, so okay, that's on conductor and insulator. Okay, let's go to the main three areas that we are interested in this chapter: conduction, convection, and radiation, and they are the ways you use to transfer thermal energy. Alright, so the first, before we begin, we have to go through some premises. Okay, so heat always travels from a place of higher temperature to a place of lower temperature. Okay, and they can be transferred in these three ways: conduction, convection, and radiation. Okay, now you may want to make a side note, and just conduction has to do with vibration. Okay, so as long as your particles can vibrate, as long as you have particles vibrating, you can transfer heat by conduction. But of course, particles that are closely packed together is always a better medium for heat to transfer through conduction. Okay, and that's solid. Convection has to do with fluid. Your particles need to be able to move around, so that's like solid. Solid is out of the question because they can only be vibrating at fixed position, right? But for liquid and gas, okay, you have them moving around, be it sliding past each other or like moving randomly. All right, and that's fluid. In physics, when I talk about fluid, I mean liquid and gas. Okay, for radiation, it transfers energy by means of EM waves. Okay, so if you don't know what's EM at this moment, it's fine. Just think of it as waves. Okay, and it transfers energy through waves. Okay, unseen waves, invisible waves. and that's how radiation transfers heat, and therefore it can penetrate through any medium, be it solid, liquid or gas, or even vacuum.